Hello, everyone. My name is Josh. This is the third installment of my review for the thermodynamics of alloys and phase diagrams 2DO3. I'm a materials engineering student at the University of McMaster, and in this video, I'm going to be going over what a miscibility gap is and how we can use it to understand phase diagrams a little bit better. So before we get into the miscibility gaps, I really want to go over this concept that I did in the last video. This concept says, when two or more phases coexist together in equilibrium, so if we were to be in a phase diagram and we were to say have a liquid and a solid together in equilibrium, the partial molar Gibbs free energy of all coexisting phases are the same. This means if I were to have that solid and that liquid in a phase together, the partial molar Gibbs free energy for, let's say, component B for the solid is the same as the partial molar Gibbs free energy for B of the liquid. If we were to now expand this and make each side RT ln of the activity of each phase, we can see everything cancels out, and the activity of B in the alpha solid phase is equal to the activity of B in the liquid phase. So when we have two phases coexisting in equilibrium, they have the same activity along with the same partial molar Gibbs free energy. And that's what we're going to investigate today. So, miscibility gaps. Starting off with this very, very simple example. Our green line here is an example of a ideal Gibbs free energy curve. Oops. So I'll just show you what that parabola looks like. Just ignore the other lines for now. So that's number one. That's that parabola, ideal Gibbs free energy. Parabola 3 down here is an example of a non-ideal Gibbs free energy curve. And so is parabola 2. Now, if we decide that we want to investigate the partial molar Gibbs free energy of each model, what we can do is exactly what I did here. At whatever composition I want. I could have done this at any point, but I'm going to do it right here when we're in equilibrium at the minimum. The composition at each point, if I take this tangent line with respect to that, when I get to the y-intercept, this is the partial molar Gibbs free energy of mixing of B, since we have all of our B components. That's the partial molar Gibbs free energy of B for each example. The blue dot is the partial molar Gibbs free energy for 1. The green dot is going to be the partial molar Gibbs for 2. And the blue dot, and the purple dot is the partial molar Gibbs free energy for 3. Sorry, I messed up the numbers. Blue is 2, green is 1, purple is 3. Okay, now, based off of what we know the green is ideal and the blue and the purple are non-ideal. Let's compare their partial molar Gibbs free energy. So the partial molar Gibbs free energy of 1, our ideal, is less than the partial molar Gibbs free energy of 2, but it's greater than the partial molar Gibbs free energy of 3. Now, what can we say about this? Well, we know that the purple line, line 3, has a lower partial molar Gibbs free energy. And what do we know about the partial molar Gibbs free energy? Well, it's equal to RT ln of our activity coefficient plus ln of our composition. Now, let's try to compare activity coefficients now. We know that in an ideal phase or an ideal scenario, right? If our mixture is ideal, we know our activity coefficient is 1. Now, if we go up to our partial molar Gibbs free energy equation here, we can see that having an activity coefficient of 1 will cancel out this term. This is also known as the Gibbs excess term. This one is the Gibbs ideal term. All three of these partial molar Gibbs free energy are going to have the same ideal term. This is because each of these are going to have the excess term plus the same ideal term. The difference now is our non-ideal mixtures have a different excess term. We can see that since the Gibbs free energy of curve 3, the purple one, is less than the Gibbs free energy of the green one, the ideal, we know that our ln of gamma term is going to have to be negative. Now, how can we get this ln gamma to be negative? Well, we have an activity coefficient less than 1. Let's do that same scenario with the blue curve. We know the blue curve is above the ideal green curve, so it's going to have an extra positive term. How are we going to gain this extra positive term? Well, that means our gamma is going to have to be greater than 1. A gamma less than 1 corresponds to negative deviations, or an enthalpy of mixing less than 0, or exothermic, while an activity coefficient greater than 1 corresponds to positive deviation, or a molar enthalpy of mixing greater than 0. All right. From here, with the help of our activity coefficient, we can understand what each enthalpy looks like. Let's take, for example, the one that is positively deviated. The molar enthalpy of mixing is greater than 0. This means that whatever it's equal to, the equation that our enthalpy of mixing is equal to, is greater than 0. And this term is equal to RT times an alpha term, which is our activation param or our interaction parameter, times XA, XB. And this term here is also equal to omega, our interaction parameter. All right. Now, what do we know about alpha? Well, if alpha is greater than 0, we have positive deviation, which tends to clustering. Our particles, our like particles want to go together, and our unlike particles separate. If our alpha is less than 0, we have negative deviation, and we have ordering. Our particles are going to order in terms of like and unlike atoms being closer together. Now, what does this mean? Well, we're going to be looking at the case of a positive alpha. In an ideal case, we know the molar enthalpy of mixing here is going to be 0. So when alpha is 0, we have this perfect parabola, right? This looks like an ideal mixing curve. As our alpha increases, the minimum decreases, and we start to gain these inflection points. At some alpha, which we call our critical alpha, in this case, it's equal to 3, we gain 2 major inflection points, which correspond to 2 new minimum points. Now, what do we know about the Gibbs free energy? Well, at equilibrium, the Gibbs free energy is at a minimum. But look here, we have 2 points where we are at a minimum. So what's going on there? Well, there must be 2 different species that have a minimum Gibbs free energy at the same time, meaning these 2 species are both in equilibrium. Now, Let's see what happens when I try to take the partial molar Gibbs free energy, or in other words, the chemical potential of these 2 points. Let's start with the first one. Let's say I'm just trying to find the partial molar Gibbs of A. So I draw my slope of that tangent line right to the left side where I'm going to have all A. This is the partial molar Gibbs free energy of A. Now let's do the same thing to our other minimum point. Let's see at this point what our partial molar Gibbs free energy of A is. Well, wouldn't you know? It's the same thing. And what did we just say right up here? When 2 phases coexist, their partial molar Gibbs free energy are equal. What happened down here? We had 2 partial molar Gibbs free energies that are equal. So what we can say, what can we say here? 2 phases coexist. This is seen by the method of common tangents. We can see if there is a spot where the tangents align and there's the same partial molar Gibbs free energy at one point, these 2 phases are in equilibrium. Now let's kind of exaggerate this a little bit. So I'm going to draw the same thing, but I'm going to exaggerate my my lines a bit more. Okay, so we had something that looked like this. And we said that there was a point on both where there was a minimum. And at this minimum, there was a point where they had the same slope, just like that, this common tangent. Now, let's see what's going to happen as we add in more of one component. Let's see. At the start, we have no B, and our Gibbs free energy is right here. When we start to add B, this lowers my Gibbs free energy until I get to some minimum point. At this minimum point, we can say A is supersaturated with B. Now, if I keep adding B, this Gibbs free energy curve is going to go up. And then it's going to start decreasing its energy. And then we're going to get to a point here. At this point, we're going to have a spot where B is supersaturated A. And that's seen if we start coming from now. Maybe we'll not use that color. Coming from this side, when we have all B, we're going down, 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 down. B is supersaturated with A. Now, what's going on over here? Well, we know that we have our common tangent. So we know that 2 phases coexist in equilibrium. What I'm going to do is I'm going to say, okay, my goal is to ride the lowest Gibbs free energy at the current point where I am. I can ride, my options are I can ride up this curve and increase my Gibbs free energy, or I built a nice little bridge for myself that has a very low Gibbs free energy. So I want to keep my low Gibbs free energy, so I'm going to go across this bridge where I can maintain my lowest Gibbs free energy. Within this region, where we have 2 phases, is called our miscibility gap. Our miscibility gap says that we are at a point where we can no longer dissolve any more of one component into the other. So since we're at this part where no more can dissolve, our two components separates, and we get a little bit of our A and a little bit of our B. So I'm going to show you what this looks like again. I'm going to take away the lines a little bit now, and I'm going to go over another different explanation. We'll take away some of the arrows. Hopefully I've driven my points. Oops. Okay. So when we're in this region, we can say that anywhere in this region, we're going to have some A rich solution. When we're in this region, we can say that we are going to have one single B rich solution. When we are within this miscibility gap, within here, our two mixtures that we can have, our A rich and our B rich, are going to separate from each other. And I'm going to have part of it that's going to be A rich, and I'm going to have part of it that'll be B rich. Let's look at some examples. I don't want to look at these just yet. Some example here. So let's see what's happening at this temperature. I'm in one phase. This is rich in C3H6O2, whatever that compound is. When we get to this point, this solution containing the richness of the C3H6O2 is now supersaturated in CS2. And the CS2 rich region, which is over here, a CS2 rich solution is going to separate from a C3H6O2 rich solution. So we have two solutions. Let's do one more. Over here, let's examine what happens at 500. We have a gold-rich solid here. We have a nickel-rich solid here. When we add in a certain percent of nickel, or we add in a certain percentage of gold, our solid that we have phase separates. In this left region, we have more gold-rich metal, since we're closer to the gold-rich phase. And over here, we have more nickel-rich metal, since we're closer to the nickel-rich phase, or the nickel-rich solid. Okay, now let's go back up to this chart here, or this one. Like I said before, there's some alpha associated with each of these curves. There's going to be some critical alpha where our inflections start to form. This critical alpha happens at a certain point. It happens when the derivative of the Gibbs free energy with respect to one component is equal to its second derivative, which is equal to its third derivative, which are all equal to 0. At this point, there is some critical temperature that we can examine corresponding to omega, our our interaction parameter divided by 2 times the ideal gas constant. And this critical temperature says anything underneath this, we are at some kind of miscibility gap. Anything over 1000 Kelvin, we have no miscibility gap, which means our components, they're fully miscible. They can mix. What happens to our activity? Well, you can see that we have a point where our activity increases and then it decreases past a point. And then it starts increasing a little bit more again. I'm going to draw another graph. So this is what a miscibility gap looks like in terms of an activity curve. We have a certain point where our activity curve crosses 3 times. It crosses once going up, once going down, and then once going up again. In between these 2 points where we cross this line going upwards, this is the miscibility gap. This is how we can find miscibility gap compositions using our activity. And what's going to happen inside a miscibility gap? Well, we know that the activity is going to be constant. So we can draw this straight line. We can do kind of the same thing on these ones as well. Right? Hopefully that makes a good amount of sense. And with all that being said, we are finished with the concept of miscibility gaps. I hope you all enjoy this video. Stay tuned because in the next video, we're going to be going over standard state, how to find a standard state, and given different standard states, how to draw activity graphs. Thank you.